People, I'm going to make this quick. We're doing the electricity review, okay? Here we go. First of all, this is a wire. The inside is metal, the outside is rubber. Rubber is an insulator. What is metal? Metal is a conductor. That's right. Rubber does not allow electrons to flow. Metal does allow electrons to flow. If we can get a lot of electrons to pile up in one place, that type of electricity is called static because it is not moving. Then if someone gets near this, the electrons will jump. Once the electrons jump, that's called a current. Okay, once the electrons arc and go somewhere else, that's a current. Why would the electrons go somewhere else? Because this place is different. This place over here has positive and negative charges. This place over here has all negative charges. Electrons, everything wants to even out. So these electrons will jump. Well, when this balloon gets near here, these electrons that are already over here will be pushed out of the way, giving this side a more positive charge, and then boom, we have that jump, right? These two being near each other, that's called induction. Induction, okay? How do we create a static charge? Well, we can just take something that's insulated and we can rub it against something else that loses electrons. So we can take an insulator like rubber and move it across something and it will rip the electrons off of it. That's friction. We can use friction to charge something as well. So you can touch something, that's conduction. You can rub something, that's friction. You can just get near it, that's induction. You can look at this circuit right here and I would say, hey, is this a parallel or is this a series circuit? And you would say, this is a series circuit because the electrons have to go through both of these in a row. In a series circuit, you add up the resistance. So I would ask you, what is the current right here? The current right here is 0.04 amps. V equals IR. You end up with 12 divided by 300. Something you should know is the current everywhere in a series circuit is the same. V equal IR, that's called Ohm's law. Ohms are the units for resistors. Volts is the potential difference across a circuit. And I is measured in amps. Now that we know this, I could ask you another problem. I could say, hey, we've got 0.04 amps flowing through this. What is the voltage across this bulb and what is the voltage across this bulb? Okay, what we do is we do V equals IR at each place. So we know the R here is 100 and the current everywhere is 0.04. So 0.04 times 100, you have 4 volts right here. And if you did the same math right here, you would have 8 volts right here. Isn't that easy? 4 volts and 8 volts adds up to your original 12 volts. Next thing we would do is look at this parallel circuit. What does parallel mean? It means that this wire right here is touching one side of the battery, and this wire right here is touching the other side of the battery. So everybody has full access to the battery. These bulbs would burn more brightly. These bulbs in a series are dim. If you started adding more bulbs, it just getting more and more dim till they all went out because there'd be too much resistance. Right here, you can add more and more lines across the parallel circuit, and this thing will just put out electricity as hard as it can go. These would be bright, okay? Now, these two bulbs are in a series with themselves, but they're in parallel with this bulb. So I'm going to ask you some questions about this. I would ask you, what is the voltage drop across this bulb? What is the voltage drop for that bulb right there? What is the current there? What is the current there? What is the current there? All right. First question, what's the voltage drop here? That's 12 volts because it's connected straight to the battery. What is the voltage drop here? Well, we're going to have to find out the current, what the current is. If we look right here, we've got 100 volts from here to here. The total resistance is 100 plus 100, so 200 ohms of resistance. So we'd have 0.5 amps. So if we have 0.5 amps right here, then we can calculate the voltage. V is equal to IR. V is equal to 0.5 times 100 ohms. So we'd have 50 volts here. And if I'd asked you, there'd also be 50 volts for this bloke. 50 plus 50 equals 100. This one right here, what's the voltage there? Ooh, I said 12. It's 100. Duh. I was imagining we were using a battery. What is the current here? V equals IR. This thing's got 100 volts coming. We know the resistor is 400 ohms. So the current is 0.25 amps. So 0.25 amps here. There's 0.5 amps right here. So 0.5 is going here. The 0.25 is going here. What is the current right here? 0.75 amps. Let's keep moving. Here we have a combination circuit, okay? You got 120 volts. You have three 400 ohm bulbs that are in parallel, and they're right in the middle of your circuit. And then they're in a series with this 200 ohm bulb. This is a combination circuit, so you have to be able to answer this. What is the first thing you should do to solve this? That's right. The first thing you should do is think about all three of these bulbs as being one resistor, and then you'll be able to answer all the questions. What's the resistance of this whole part of the circuit? Okay, the total resistance for this is 133 ohms. There's the formula there. There's how I did it. All right. So now, let me ask you a question. What is the current right here? All right. The current right here is 0.9 amps. You can freeze your screen and see how I solved that. Nope, I made a mistake. Stop. Look what I did. I wrote 133 ohms because that's the resistance right here. This whole thing acts like a 133 ohm resistor, but I forgot this 200 is a series. So 300, I had written that down and erased it. 333 ohms is the total resistance. So that's wrong. It should be 120 volts divided by 333. 0.36 amps. 0.36 amps. Okay, I think I've made that clear. You have to add up this plus this for your total resistance in the circuit. So 0.36 amps there, 0.36 amps there. What is the current right here? Well, the 0.36 amps goes through this, this, and this. It's split three ways, so it'd be 0.12 amps right there. Do you agree with that? The last thing I asked you, what is the voltage here and what is the voltage here? This whole thing acts like one 133 ohm resistor, okay? So V equals IR right here. V is equal to 0.36 amps across this whole thing and 133 ohms. So the voltage right there is 0.36 times 133. The voltage here is 48 volts. And then the rest of the voltage would go right here. 72 volts. All right, good luck with that. Let's keep moving. You've got an oven in your house that uses a lot of electricity because you're cooking on it, right? Anything that produces heat uses a lot of electricity. What is the amperage running through your oven? Your oven's hooked up to 240 volts at your house. So what is the amperage? You would say, okay, I've got a 2,000 watt oven. What is the amperage? All right, 240 volts. How many amps are going through that? 2,000 divided by 240. 8.3 amps. All right, next question. It's Thanksgiving. Where you live, it's 14 cents per kilowatt hour. How much does it cost to run a 2,000 watt oven for 3 hours? Go. It costs you 84 cents to cook that turkey. Here's a coil or a solenoid. I want to get this light bulb to light. What do I have to do? That's right, you got to move the magnet. Now let's say I drilled a hole in this magnet so it could spin around. Describe the type of current that would be created in this coil. That's right, it will be an AC current. because as the north side went down, you'd get one direction of current. As the south side went by, you'd get another direction of current. That's right. I've got a nail, I've got a battery, and some wire. What can I create? An electromagnet. How can I make it an electromagnet? That's right. I could take the wire, hook one end up there, wrap it around a nail a bunch of times, hook it back up to the battery. Now we have an electromagnet. All right? Let me ask you a question. How can I make this electromagnet stronger? That's right. Could use a stronger battery or more wraps. Exactly right. Now I get rid of the battery and I hook up an AC current. Would this still be an electromagnet? No, because the current would be switching back and forth. That wouldn't be any good for us, but we can do something with this. All right, I've got a 120 volt AC source with 10,000 wraps on one side of an iron ring. What am I building? Yeah, I'm building a transformer. Okay, next thing. How can I get this 12 volt light bulb to work properly? We're going to say this guy right here is putting out 5 watts of power. How can I get this 12 volt light bulb to work properly? That's right. I can take a wire and I can give it 100 wraps. I'll give it 100 wraps. What am I changing? I'm changing the voltage. I'm going from 120 to now 12 volts. This has 1,000, excuse me. This is 12 volts. So I've got 1/10 the wraps and we have 1/10 the voltage. What stays the same on each side of the transformer? That's right, the power. So the power is the same on each side. So if I've got 5 watts and 12 volts, what is the amperage running through this bulb? That's right. 12 times what equals 5? So 5 divided by 12 equals 0.42 amps. Good job. These two coils are very similar. Would this light bulb be on right now? No. Why would it not be on? Because this is a DC current. We need an AC current. All right? What does an AC current do to the magnetic field in this coil? You're right. It makes it switch from south-north to north-south, back and forth. Making this magnetic field switch back and forth is similar to doing what near this coil? That's right, similar to moving a magnet. So this is wireless electricity, and it only works on AC. I have 2 parallel plates that are 12 volts, and the distance between these 2 plates is 5 millimeters. What is the electric field intensity between the 2 plates? 2,400 volts per meter. If I'm going to draw electric field lines in this battery, what would they look like? Which direction would they head? They would point down and they would be evenly spaced as long as we were not near the edges, okay? How does this battery store energy? Correct. It's got electrons that want to go somewhere else. Which one of these electrons has the most potential energy? That's right, this one does, okay? Which one of these electron feels the most intensity from the electric field? Which one of these is experiencing the most force, or which one of these is moving the fastest? That's right, they're all the same. This guy's being pushed really hard because like charges repel, but he's barely being attracted. Well, this guy's being pulled really hard while barely being repelled. And this guy's got like a pretty even amount of repulsion, but they all add up to the same thing. All right? If I had 1 coulomb of electrons, how much work could this battery do? That's right. It could do 12 joules of work, right? 1 volt is equal to 1 joule of work being done per 1 coulomb of charge. That's exactly right. How will I draw the electric field lines around this guy? You right? Away, evenly spaced, and 90 degrees to the surface. How would I draw electric field lines around this guy? Okay, that's right, towards it. And tell me about these two guys now. That's right, they are attracted to each other. This is a 0.007 Coulomb charge, and this is like a little electron or a proton out here in the electric field. What is the electric field intensity if we are 9 centimeters away from this charge? What is the electric field intensity right here? It is 7.8 times 10 to the 9th coulombs per meter squared. One last question. Are these two guys attracted or repelled? That's right, they repel each other. And if we draw electric field lines, we will see that they turn away from each other like this. That shows the repulsion. You can tell they're positive because you see the arrows going away from them. Last question, I mean that. This is the very last one. If this is a 0.009 Coulomb charge, and this is a 0.084 Coulomb charge, with what force are these two guys pushed apart, according to Coulomb's law? If the distance between them is 11 centimeters, or 0.11 meters. Wow, that's a really, really strong charge right there. And there's the formula for Coulomb's law. Good luck on tomorrow's test, or good luck learning this.